Okay, yeah, sure. So this is the last slot of today's session. Paul Wilson will give us a talk about reverse derivative ascent, a categorical approach to learning Boolean circuits.
Cool. So I guess I should start by thanking the organizers for a really good conference. So this is some work that I've been doing with Fabio Zanasi at UCL. And the general idea is that we want to use parameterized Boolean circuits as a class of machine learning model. And we want to train them in the same way that you would train a neural network. So what's a parameterized Boolean circuit? It's just a circuit where we say that some of the inputs are parameters. So here's an example. The two betas are parameters, sorry, and we're trying to learn a function that maps a 1-bit input to a 1-bit output. Okay, so in general, there's sort of supervised learning setting. We're given a data set of examples, so input-output pairs X and Y, where our inputs are A-dimensional and our outputs are B-dimensional. And our goal is to find a function that maps from the inputs to the outputs, and it should be roughly like the data somehow. So the first thing we have to do is choose a model, and this is basically, as we saw earlier, a parameterized Boolean function. So it's a circuit where some of the inputs are parameters, and basically the parameters function like an index into a function space. You can kind of think of it like that. And so we're going to try and search for some parameters that, when we partially apply to our model, we get a function from A bits to B bits. And again, hopefully that should kind of approximate the data in some way. And this is exactly the same as the setting for neural networks, except that in neural networks, obviously, we have real numbers, and our model has to be differentiable. And also for neural networks, we have got an algorithm to find this parameter vector, whereas, of course, in circuits, we don't know what that is. That's kind of the point of this talk. So I'm going to start by trying to motivate why you would even want to use circuits as a model class. There's a bit of background, because essentially our work is like a synthesis of two other papers. Then I'll talk about our algorithm, reverse derivative ascent, and then I've got a little demo at the end. So, okay, so why would you want to do this? Well, you may have seen the headlines, various headlines like this AlphaStar program by DeepMind, which is beat the kind of top StarCraft players. There's GPT-3, which you may have heard of recently, which you can feed it some like a text prompt, and it can do a very like human completion of it. So that people have used it to write poetry that looks quite good. But these models, these state-of-the-art models, they have a problem in that they're enormous. So AlphaStar, for example, they had something like 200 years of playtime per agent. It cost 30 million. This is an estimate. It costs about $13 million to train. It's obviously very expensive. GPT-3, the trained model, so assuming you've trained it, it's got 175 billion parameters, which means nearly a terabyte of data just to store the parameters of the model. And so if you wanted to just run that model forward, not retrain it, and you wanted to run it on a machine in the cloud or something, that's like $30,000 a year. So it's very, very expensive. And I think that the point of this is that this kind of GPU hardware and so on has been taken advantage of by deep learning to sort of get to these impressive feats. But now that we're sort of hitting hardware limits, the models are growing faster than the hardware, we sort of have to try something else. And so there's one idea in the literature, it's this thing called binarized neural networks. There's a bunch of different schemes, but the general idea is that we take a neural network and we constrain the weights to be -1 or +1. So this is how neural networks are normally depicted. So you can think of it kind of like an open graph. So on the left, we have inputs. On the right are the outputs, and the inputs flow through here, and they get multiplied as they go along these wires with the parameters, these weights, and then all the values ending up in these nodes get summed together. I'm not a massive fan of these diagrams because I think you can draw them as string diagrams. So why would you do this? So one of the early papers for binarized neural networks is called Binary Connect. They basically said, well, if your weights are -1 or 1, then instead of having to do an expensive floating point multiplication for this input, you can just check if this is -1, then you flip the sign, or if it's +1, you do nothing. And then these expensive multiply, accumulate, dot product operations just become sums. So it's much bigger. There's another really nice paper. It's called LUTNet. And I think you can sort of look at this paper as extracting a circuit from the trained neural network. One other interesting thing that they observed was that not only can you extract this circuit, but you can sort of train it in such a way that you can turn what are sums in of bits into kind of these nonlinear lookup tables. I don't want to go into too much detail about that, but the point is that they kind of showed that you can sort of extract a circuit from this. And actually they run their circuit in an embedded setting, so on an FPGA. And this is quite an important thing to want to do if, for example, you have like a machine vision application where you need to, in real time, do some kind of object recognition algorithm of images. You want your algorithm to run quickly in a low power setting where you don't have access to this kind of big hardware. So kind of just to take a step back, the kind of abstract view is like this. We're on this top layer here. We start with our untrained neural network, where we have a p-dimensional vector of reals, that's our parameters, an a-dimensional vector of reals, that's our input. We produce b-dimensional outputs. And in training, we just find some parameter vector and we cap off the parameter input to our neural network. And so our trained neural network is a function from a dimensions to b. And then circuit extraction is kind of just like turning these reals into bits. That's a bit of an oversimplification, but that's kind of what we're doing. So the kind of obvious question at this point is, why don't we just do this? So we start with a circuit and we train in circuit land. And that way, we never have to deal with real numbers at all because they're messy and floating point is difficult. And one of the key reasons you might want to do this is because in both of these previous approaches, you need to have a real valued gradient. So when you do your training, you still need real numbers floating around. So it seems like it's quite difficult to port that training to an embedded setting if you still need this floating point operations. Okay, so to understand how we might do this red train arrow here, we sort of have to understand what training a neural network actually does. And this is a very oversimplified view of stochastic gradient descent for neural networks. But the general idea is that you take your current best guess for the parameters, and you have an example from your data set, so an input and output there. You feed your parameters and your input data into the model, and you see how the model's prediction compares to the true label. And you take the difference, and then you feed that difference into automatic differentiation, which tells you how you should change your parameters to sort of more accurately reflect the example you were just showing. And automatic differentiation basically just computes the gradient of your model. So to port this to circuits, we need two things. First, we need a notion of circuit, obviously. And second, we need to somehow port that automatic differentiation gradient business over as well. So luckily, someone's done the first thing for us. This really nice paper, which sort of does like a string diagrammatic view of circuits and sort of builds them up from the ground up. It's very good. But to very quickly summarize it, we take the classical circuits from this paper, and those are kind of the digital circuits you would expect to see in your CPU. So it's like you can do nothing with an input, you can discard its value, you can copy the value on a wire. There's a constant zero function, you can add things together. This is exclusive OR. There's a constant one function, and there's multiplication, which is an AND gate. And also we have equations for these, which are kind of what you might expect. So we have the commutativity for adding and multiplication, associativity, units, and same for copying. It's Cartesian, so this is any morphism F. We have these properties. And then we have these equations down the bottom, which are sort of specific to the field we're in. And in particular, this one here, this is saying basically x squared equals x. So if we have an input x and we multiply it itself, then we might as well have just left the input as is. And this is going to be kind of important in a minute, so that's why I'm going to that. Great, so we've got some notion of circuits. Now we need some notion of gradient or automatic differentiation for circuits. luckily someone's done this for us as well. So this is a really interesting paper that came out last year, late last year. And actually the authors, I think some of the authors are giving another talk later today, so you should check that out. But this is basically a category theoretic axiomatization of the gradient in neural networks. So it basically generalizes it and lets us talk about that same kind of operation in different categories, which is exactly what we want, of course. I'm not going to go into it in too much detail, but the intuition for this is it's kind of like it takes a morphism and gives you a morphism that does this. So if I have a given input for my function and I want to change my output in this way, so this should be like how I want to change my output, then it will tell you how I should change my inputs to achieve that change in output. It's only an approximation of this, and obviously this is not possible to do in general because some morphisms like discard there's no way you can ever change your output. But in general, it's like an approximation of answering this question. And luckily, they also give us a reverse derivative for a category which is quite like circuits. So it has objects, natural numbers. Morphisms are the B tuples of polynomials and A variables. But for us, this just means it's basically circuits without this x squared equals x axiom. And that kind of makes sense because obviously polynomials don't have that. So what does this mean graphically? Well, here's how we define it. And maybe to give some kind of intuition for why it's defined this way. So if we take the identity, this is saying for a given input and a desired change in output, how should we change our input? Well, for the identity, we want to change our output, we should always change the input, right? That's sort of obvious. Same for the twist here. And for discard, obviously we have no output, so you never need to change your input because nothing's going to happen. This is the constant zero, remember? And of course it's defined on composition and tensoring like this as well. Oh, and this is the reverse chain rule. Cool, so we have this definition on circuits and we can just apply it, right? Well, not quite. So because we have this axiom of circuits, x squared equals x, we know by definition that the reverse derivative applied to identities is this thing, but we know that this is the identity by this axiom. And if you simplify, if you take the reverse derivative using the definition on composition, then you can work out that it's this. And these are obviously not equal, so that's a problem. We can essentially fix this just by forbidding a square to appear in your circuit. And you can do that combinatorially just by saying like that the circuit inputs reachable from here are not the same ones reachable from here. And because every circuit has a safe equivalent, you can always apply your reverse derivative this way, and it's well defined. So now that we have that, we can actually define our algorithm at last. And so this should look familiar from the earlier part where we talked about stochastic gradient descent. It's basically the same thing, except now we can fill in the blanks. So for a given current best guesser parameter and a given pair of input and output example, we feed the parameter and the input into the function. We take the difference. And obviously, because we're in Z2, elements are self-inverse, so we can just add them. But if you're in a different setting, you might need an inverse on one of these y's. But the point is, the output of this thing is basically a bit vector of b bits, which says in which places our output was wrong. So it's 1 if it's wrong. And then we feed that into the reverse derivative, which tells us how to update our parameters. And this will, if we sort of zoom out, this will compute a slightly better parameter vector, we hope, than the current one for the given example. And so to apply this to a data set, we just need to unroll a loop. And we have this. And really, this is just the scan operation on this inner loop. I've just kind of unrolled it here, so it's a bit more visual. But we start with some initial guess for our parameters, which can just be 0. And we show it examples from our data set, and we get a sequence of hopefully improving guesses. So this is nice, but if we don't test it, we haven't really done anything. So here's an example from the paper that we ran it on. This is kind of a famous-ish machine learning benchmark, which pretty much everyone runs their machine learning algorithms on. It's a 28 by 28 pixel image, and it's obviously like a digit in the range 0 to 9. This is just a sample of the data set, but the idea is you predict what digit is written in the image. The pixels in the image are 8-bit integers. So I think, oh, sorry. So we're doing this smaller subset. We're just focusing on this binary classification problem instead of the full 10 class one. So yeah, what I was going to say is the first thing we do with this data set as well is we pre-process it. So that those 8-bit pixels, we just crush them down into a single bit, which is 1 if the pixel is, the value is larger than the average pixel value across the whole data set. And the reason we do that is just because otherwise we have to start including complicated machinery to figure out what's the meaning of an 8-bit number, and this is just a bit simpler. So we have a simpler problem in some ways that it's binary classification, but in another way we've thrown away a lot of information in the input data. But anyway, so that's our pre-processing, and then the model that I chose for this problem, it's very simple. Basically, the parameters to the model is another 28 by 28 image, and you kind of overlay that image on top of your input image. You multiply them together, and then you see how many bits are left, and you just count how many bits. And so the idea is that you will find the bits that are common to one class but not the other. So here in this example, you can see it's kind of learned the 1 bits in a 0. So these are bits where zeros have those bits, but ones don't, if that makes sense. This does quite well. So we get 99.2% accuracy on MNIST. Again, it's the 2-class problem. I think the state of the art is something like 99.8 on the full problem, but again, they used all the bits in the input. So it's not exactly an apples to apples comparison, but anyway. So yeah, that's our model. I guess I'll show a quick run of it. So this is exactly this model I've talked about here. And I put in an artificial delay. Hopefully this isn't too janky, but you'll see this accuracy number should change, and you should see that there you go, the feature mask change as well. This model is not amazingly great for demoing because it tends to make these big sudden jumps. So in a minute, you should see it jump up to something like 98 or something like that. And again, I put in a delay here, so usually it's a bit faster, but just so it doesn't spam the screen. There we go, and the feature mask has changed again. And notice on a lot of these iterations, it's actually not changing the parameters. But if we want to see maybe a slightly more interesting demo, this model is not as good in terms of accuracy, but it's a lot more interesting to watch in a demo. So I'm just going to run this one in the background. You'll see it wobble around a lot. The accuracy is very kind of, it's got high variance in it, but it's doing a lot more changes to the feature map. This model is basically the same thing, except instead of counting the bits, it has a lookup table for the number of bits, mapping the number to a 0 or 1. This is the parameters that lookup table, but it's not very interpretable. So yeah, that's our paper. I'll leave this running in the background, I guess, and I suppose questions.
Let's thank the speaker for the talk. Great. So there are a couple of questions on the chat. Maybe Bruno wants to go first.
Hi. Yeah, thanks for the interesting talk. So I was wondering about this inner step of the algorithm, the diagram you showed. Can you go back to it?
Can you see my slides? Is it showing?
Yeah.
Okay.
So right. So I'm wondering about the top right operation on what I assume is a parameter and its corresponding gradient.
This part.
Right. So we are here like XORing them.
Yeah.
And right. So I guess I'm wondering about the interpretation of why is this the particular choice of the operation and not adding, for instance. And
So
I guess generally, why is it also ascent as opposed to descent, which is in neural networks?
so okay, so the first question is, why is it exclusive ORing? Exclusive ORing in this is adding, right? Because we're in Z2.
Right, right.
So it's basically just adding the change in parameters to the current parameters. It's kind of weird because it's like bit flips, so it doesn't feel like addition if you think about it in terms of like flipping bits. But yeah, it's the addition in this category.
Right, but wasn't there another operation you defined, the white blob?
Yeah, that's multiplication. That's and.
Oh, right.
Yeah.
I guess I'm wondering why is it not that? That's what I meant. Yeah.
I guess so. Oh, I see. Right. So I guess you view these parameters as like a change. So something you would add to your initial guess to get the new update. I guess that's my answer. I'm not sure that's very satisfying.
Yeah, I guess it makes sense. Yeah.
Okay, there are a few more questions. We have a few raised hands. Maybe Jules wants to go first. Jules has a short question, maybe.
I think that was a comment disguised as a question, but I was.
Okay.
I thought it looked like Haskell, and I was expressing surprise that you're doing machine learning in Haskell.
Yeah, it is Haskell, and I don't know. I'd rather do it in Haskell than anything else. So.
Okay. So maybe Alex wants to ask a question.
Yeah. Thanks for the talk. That was really interesting. I was wondering, like, do you have a feel for how much you lose by the fact that this space is so discrete? I mean, the fact that you're really having to hop between zeros and ones rather than being able to sort of interpolate your way toward a solution?
I mean, the short answer is no, I don't really have a feel, but I was actually kind of surprised this worked at all, because a lot of the, I've seen a few quotes in various binarized neural network papers where they say things like, it seems like real valued gradients are necessary for this to work at all. And so I was like, well, I'll give it a shot and see if it works. And it's kind of surprising that it even goes anywhere. So no is the short answer, but it also seems that maybe by flipping bits, you can make very large jumps to maybe escape local minima. That I don't know. I feel like maybe I definitely don't understand the behavior well enough to give you a good answer there. So.
Okay, so Geoff Cratwell has a question.
Yeah, thanks for the talk. Just a comment and a question. So comment, first of all, I think it's a really cool new example of a reverse derivative category, because, I mean, at least from my perspective, I wouldn't have thought of doing something like a reverse derivative category with kind of binary circuits. So it's a really cool new example, I think. I guess the other question is, you mentioned a bit in the paper that the reverse derivative ascent you can define here, you can do for any reverse derivative category. And so my question was, have you proved any kind of abstract properties of this operation in general?
Oh, so you're talking about, for example, like convergence. Would it actually get to a good answer in general?
Yeah, like, I mean, there's lots of properties that the reverse derivative has. Can that tell you, inform any properties of this reverse derivative ascent?
That's a good question. I think there's, so you have this like additivity thing with reverse derivative. So I think maybe there are different schemes that you could use for updating your parameters. One thing I've noticed is that sometimes the reverse derivative will suggest like multiple bit flips to update, but they're sort of contradictory. So flipping both of them actually gets you to the wrong answer, whereas flipping one would get you the right answer. And so I think that suggests maybe like doing one bit at a time scheme might work or something like that. But as for the part about different settings, I think this needs a bit of a tweak for, as I said, like inverses here. Did I answer your question?
Yeah, I guess, yeah, I mean, yeah, I just worried about in general. I guess in general, I was sort of thinking maybe you need subtraction to,
oh, right,
I mean, yeah, in this case, addition kind of equals subtraction. So maybe in a general reverse differential category, you want to have subtraction with it, and then change the reverse derivative sense so it uses subtraction, and then see what kind of properties that might have in general.
Yeah, I suspect you're probably right, yeah. But I didn't want to say for sure, because you know, you never know what like weird example might come out. So.
Yeah.
Okay, there are a couple more questions, but I'm afraid our time is up. So maybe the question should be referred to the speaker later at another medium. So let's first of all thank the speaker again.